If you have a ball launched from a cannon to hit a specific target, and you know how far away the target is and how fast the ball was traveling, you can use this to calculate the launch angle of the ball, theta. For this problem, we'll say that the ball has an initial velocity of 10 meters per second and travels a distance of delta x of 10 meters. We'll say that delta y is equal to 0, meaning that the ball ends at the same height that it started at. In this situation, we can use the range equation. Delta x equals velocity squared times sine of 2 theta, which is the launch angle, divided by g, our gravitational constant. I'll show you exactly how to derive this equation next. Given our initial velocity vector of 10 meters per second and the desired launch angle theta, we can break this into our horizontal and our vertical components. The horizontal component, the velocity in the x direction, is given by initial velocity times cosine of theta, and the vertical component is given by initial velocity times sine of theta. Let's first examine the velocity in the y direction. Other things we know about the y direction is that we have the gravitational constant of 9.8 meters per second squared for our acceleration. We also have our delta y is equal to 0 from our initial problem. We can use these three variables to find time. Using the equation delta y equals velocity in the y direction times time plus 1/2 acceleration in the y direction times time squared. We can turn this into 0 is equal to initial velocity times sine of theta, which is just plugging in our value for Vy, times time minus 1/2 gt squared. We're using 9.8 meters per second squared for our g. Notice the negative here, implying that acceleration is in the negative direction. From here, we can pull out one of our t's. Pulling this out and changing this into t to the first yields t times initial velocity sine of theta minus 1/2 gt. From here, we have 0 equals initial velocity sine of theta minus 1/2 gt. This is just 0 equals the inside of these parentheses. From here, we can rearrange the inside of the parentheses to get initial velocities times sine of theta equals 1/2 gt by adding 1/2 gt to both sides. Finally, we can rearrange this by multiplying by 2 and then dividing by g to get 2 times initial velocity sine of theta divided by g is equal to our time, t. Now that we have our value for time, we can focus on our velocity in the x direction, the horizontal component. Things we know about the x direction are that delta x is equal to 10 meters from the initial problem, and since this is a projectile motion problem, we know that acceleration in the x direction is equal to 0. We can use these and the displacement equation. Delta x equals velocity in the x direction times time plus 1/2 acceleration in the x direction times time squared. This is the same equation we used for delta y. We can plug in our values, canceling the acceleration in the x direction since it is equal to 0, and plugging in vi cosine of theta to get delta x equals vi cosine of theta times time. Now that we have a value for delta x, we can use it along with our value for time to calculate our range equation. Delta x is equal to 2 initial velocity squared times cosine of theta times sine of theta divided by g. This comes from taking our value for time and plugging it into delta x here. We multiply across the top by 2 initial velocity and sine of theta to get an initial velocity squared, and then divide the whole equation by g. From here, we can use this identity that 2 cosine of theta times sine of theta is equal to sine of 2 theta. Notice here that we have 2 cosine of theta and sine of theta. This makes the equation into delta x equals initial velocity squared times sine of 2 theta divided by g. Now that we have this equation, we can use it along with initial velocity and delta x to calculate our angle theta. We need to rearrange this equation and solve it for theta, which I will do symbolically. we need to get theta by itself. The first step is to divide by vi squared from both sides and multiply by g, leaving us with delta x g divided by initial velocity squared is equal to sine of 2 theta. From here, we can take the arc sine of both sides, or the inverse sine, to leave us with inverse sine of delta xg divided by initial velocity squared is equal to 2 theta. From here, we can plug in our values for initial velocity, delta x, and gravity. This leaves us with the arc sine of 10 times 9.8 divided by 10 squared is equal to 2 theta. Plugging this into the calculator leaves us with 2 theta is roughly equal to 78.52 degrees. We actually have 2 theta values though. The first is of course dividing by 2 yields theta 1 is roughly equal to 39.26 degrees. To find the second, we have to recall the unit circle. Remember that in the unit circle, the first 2 quadrants yield positive sine values. This means that if there is an angle in the first quadrant yielding a positive sine value, there is an angle in the second quadrant reflected across the y-axis. We can calculate this angle by doing 2 times theta 2 is equal to 180 degrees minus 78.52 degrees. This leaves us with our theta 1 being equal to 39.26 degrees calculated from the first equation, and theta 2 calculated from the second equation is roughly equal to 50.74 degrees. As you can see here, our first angle, 39.26 degrees, gives a lower trajectory than our second angle. The second angle, 50.74 degrees, gives a higher trajectory, but they both hit the target in the same spot. The key takeaways for this video are that if we have initial speed and range, the launch angle can be found from the range equation, delta x equals initial velocity squared times sine of 2 theta divided by gravity. One important note is that this range equation only works when there is no change in height, in other words, no delta y. Finally, one target can have 2 separate launch angles, the second of which can be calculated from 2 times theta 2, which is our second launch angle, is equal to 180 degrees minus 2 times theta 1, or our initial launch angle. Thank you for watching this video, and I hope to see you in the next one.